This is your step-by-step guide to making simple custom PCBs at home on a cheap CNC router. My favorite projects are the ones where something is created that's either hard or impossible to buy off the shelf. And normally they're 3D printed, but today we're making a custom PCB using a cheap CNC router. The methods in this guide are unconventional in that they're simplified to suit this type of home manufacturing. The aim is for the process to be as quick, simple, and cheap as possible, so let's get into it. Recently I tested the BIQU BX, an Octoprint compatible printer that's currently on Kickstarter. I was able to use the printer in Marlin LCD mode, touchscreen mode, but most importantly, I could use it with Octoprint by installing the excellent third-party UI, Octodash. This gave me touchscreen control of Octoprint to complement the usual web interface. Since then, I've been enjoying the printer, including the usual Octoprint perks, so overall, I think this is a pretty good implementation apart from two things. Firstly, I was worried about screen burnout by having the LCD on permanently, but assisted by the developer and with reference to some Linux documentation, I was able to alter the configuration to have the screen automatically go to sleep after 3 minutes of idle time. Box ticked, but there was still another problem that made it less than ideal to leave this printer sitting with everything powered on. As you can hear, there's 3 fans that are going permanently that create a bit of a racket. Firstly, we have the heatsink fan connected to the hot end. We have a blower fan blowing permanently over the mainboard. And there's also this third LED lit fan at the front, which I think is mainly for show. The 2 mainboard cooling fans are plugged into ports that supply a constant 24 volts, even though there's 2 MOSFET switch fan ports available on the mainboard. So I simply plugged them into these and monitored the temperature at idle of the processor heatsink and found it was moderately warm at most. I still did want the fan to come on during printing, so I added an M106P1 to my start G-code to turn on the fan at the beginning of a print, and an M107P1 to turn it off at the end of the print. So that just left one noisy fan to address at idle, but this one was going to be tricky because of the HDMI port that went the whole way back to the main board. If we remove the hot end assembly and trace the fan back, we can see that the breakout board supplies it with a constant 24 volts. So we're going to have to intercept this wire to turn on the fan only when we need it. I then remembered a great video from earlier in the year from CHEP. In this video, he designed a simple circuit, manufactured and assembled a PCB, and calibrated the circuit to automatically turn the heatsink cooling fan on and off around 50 degrees. This would be absolutely perfect for my application, so with CHEP's permission, we're going to make the circuit in this video. This is the normal process I would follow when making a do-it-yourself PCB, following steps to design, model, manufacture and assemble. This is a topic I've actually covered in the early days of this channel, but most of my PCBs are rather simple and rely on a microcontroller to do all of the heavy lifting because I like writing code, but I'm a novice at designing hardware-only circuits. So in this case, rather than designing the circuit, I'm actually going to simulate CHEP's circuit so I can attempt to understand it properly, especially when there's variation in the components that I'll use. To achieve this, I found a website called Everycircuit, and it allows me to build a schematic and then simulate the circuit in real time, monitoring voltage, amperage, and resistance. It's free for 24 hours of use, but in my case, I paid the $15 to have a lifetime license. The usage is pretty straightforward. We click on a component, and then we drag it into position. We can click on the spanner to change its parameters. In this case, I'll set my power supply to 24 volts. Once you've got all your components out, you simply click to join them all up and hit play to start the simulation. While it's running live, you can click on a component, then come to the spanner and adjust the values in real time. In this case, I'm going to lower the value of the resistor until the LED explodes. So here we have the CHEP circuit with our 24 volt supply from the breakout board, the fan we want to switch on and off. I'm using a MOSFET as the switch, and feeding the gate of the MOSFET is a voltage divider circuit with a 100K thermistor and a trim pot for adjustment. Everycircuit doesn't actually support thermistors, but if we treat it like a resistor where the resistance drops as the temperature increases, that means we can simulate a thermistor by lowering the value as the simulation is taking place. I edited the components to reflect what I had, including a 5K trim pot rather than a 10K, and I looked up the datasheet for the MOSFET I had. It was rated for 60 volts, well above the 24 volts of this circuit, and I could see I'd need around 3 volts to switch the MOSFET on and therefore the fan as well. Let's start the simulation and mimic the hot end heating up by lowering the resistance of our dummy thermistor. You can see as the value lowers, our input voltage to the MOSFET continues to go up until the gate is triggered and our simulation tells us that the fan will start spinning. To make sure the circuit would work in practice, not just in theory, I set it up on a breadboard. If we apply a heat source to the thermistor, watch the voltage rise on the multimeter until it trips the gate, the fan gets 24 volts and turns on. Cool down the thermistor, the voltage drops and the fan turns off. On to step 2, designing the PCB. And in the past I've used EagleCAD, but for this video I'm using KiCAD because it's completely free as well as open source. And our first job is to recreate the schematic. Here's the finished one, so let me show you how I did it. Over on the right hand toolbar, we're going to come to the button that says place symbol. And when we click on the workspace, a dialog box will pop up. You can type in the filter to find what we want. Here I'm going to select a potentiometer. Now the symbol will be moving with the mouse and I click to place it. I'm going to switch back to the normal selection tool, click on my part, and then press E for edit. Here I can change the parameters to give things a name and a value. For things like power and ground, we use this button underneath called Place Power Port. Once again we click, the dialog box comes up, we can type what we want in the filter, and anything recently used will come up again. Once again click to place. To move things around, we drag a box around them, they'll then float with the cursor, and when we click they'll remain in that place. We can also select something and then use the keyboard Ctrl+C followed by Ctrl+V to copy and paste. To connect things up, we use the icon with the green line called Place Wire. It's simply a matter of clicking one end and then clicking the other. By placing your components one by one and then connecting them with wires, you'll end up with your finished circuit. If you're into electronics, you might find that I have some weird symbols and labels here, but for a homemade board, it doesn't really make any difference. What is important, however, is assigning a footprint for each symbol in our schematic. For these 3 ports here, I'm going to solder in JST female plugs to my board, and then crimp on JST male connectors for the voltage in, fan out, and thermistor in. To set this, we click on our symbol, press E for edit, and you can see here under footprint, I have connector JST-XH. When you do this for the first time and go to edit, it'll most likely be blank. So we click on footprint and then click the library button and some suggestions will come up. If you're doing a professional board, you'll probably know exactly what component you're using. For me, it was a matter of trial and error until I found a footprint whose measurements seemed to match the components that I had. When you've got what you want, double click and then click OK. Once you've got a footprint for all of your components, we're almost ready to design the PCB. Our last step is coming up to the top toolbar and clicking on Generate Netlist. I didn't change anything here, instead I just went to Generate Netlist, I gave my file a name and clicked Save. Our schematic is done, so we can save and click the green button, Run PCB New. Once again, we're looking at the finished product, so let's step backwards and see how we arrived here. When you start out, this will be blank, but now we're going to import the netlist we just created by clicking on Load Netlist. I didn't change any of the settings here, I simply went Update PCB. And when I click, all of my components are placed. Our controls are similar in that we can click and move around components to get them into position. While we've got a component selected, we can also press R or Shift R to rotate them in place. These white lines here indicate what needs to be connected to what, and it's known as a rat's nest. Our job at this point is like a puzzle, and we need to rearrange things, much like a puzzle, until the pieces fit, and this can be quite challenging. So hopefully you'll eventually find a layout where things can connect without crossing over too much. But before we continue, let's inspect a home cut board to see what we're aiming for in the next stage. If we look at the finished board, we can see where the CNC has cut, the grooves left behind are actually quite wide, and that means our actual PCB traces are a lot more narrow than we might expect. Therefore, it makes sense to add thickness to the pads and traces ahead of time to compensate for this. So to get everything as machinable as possible, let's start by enlarging all of these pads. If we double click on them, we can change the size for each, making them as big as we think we can get away with, without them overlapping each other. You can see here I've pretty much hit the max. The clearance circles don't quite intersect, so this is as big as I'm comfortable as going. It's repetitive, but on a small board like this, it shouldn't take you too long to get all of your pads enlarged. The next step in this process is coming up to the top left and clicking on Board Setup. We want to come to Net Classes and then change some of our defaults, once again bumping up the numbers. I'm going to put my clearance up to 0.5 mm and my minimum track width up to 1 mm. After that, we can confirm by clicking OK. It's now time to come to the green line, which is Route Tracks, and click it to start joining things together. It's important to make sure that your layer is the back copper layer, because so far we're looking at our board from the top, but the PCB traces are actually going to be on the underside. Now it's just a matter of clicking the start and end destination, using our Ret's Nest as a guide, and very quickly we'll have everything joined together. The only ones that I haven't done are the 3 ground pins, because we're going to treat those a little bit differently. So far our PCB doesn't have a physical border, so we're going to click on the Edge Cuts layer, and then use the Add Graphic Lines tool, and snapping to the grid, we're going to draw the outline of our PCB. Now the reason we didn't directly connect these ground pins is that in PCB design, we normally have a ground plane. We'll make sure we're on the back copper layer again, and then come down to the tool called Add Field Zones. As soon as we click the cursor, we'll get confirmation we're on the back copper, and we're going to select ground. After this, we simply retrace the outside of our PCB, and it will fill in copper around all of our existing traces, except we'll notice on the ground that the pad is connected by these 4 corners. Here's my original needed design. The only thing we haven't covered are these dimensions. We have a tool on the right hand panel called Add Dimension, and then we simply click the starting and end point to find out how big something is. So we're ready to manufacture for a home CNC. We've got oversized traces and pads, and that gives us wiggle room if we accidentally cut too deep. That's the hardest work over, so on to step 3, making the PCB. We're ready to export our files for manufacturing, so we're going to come up to File and then Plot. Now the default format for exporting for professional manufacturing is a Gerber file, but I'm not going to use that here. Instead, I'm going to use a graphic format in DXF. And that's because my original PCBs involved printing an etch mask on a laser printer. There's only 2 layers that we care about, our back copper as well as our edge cuts. I'm going to change my units to millimeters, and I'm going to set my drill marks to actual size. After this, I can simply click Plot. The software we'll be using to create our CNC toolpaths is called Carbide Create, and once again, it's completely free. When it first opens, you should come up to the settings gear and check your units are set correctly. We can now come to Import, which is the second icon, Export External File. I select my back copper DXF and move it up right near the origin of the document, which is in the lower left hand corner. We now click Done. An extremely important next step is to highlight all of our geometry and then perform a horizontal flip. Remember that in KiCAD we were designing our PCB from the front, so what's on the back should be mirrored before it's cut. We can now come to Toolpath, and we're going to click on Contour. Now the default tool is no good for what we need, so we need to click Edit, and then Change Tool. And you can see here I have my own user set of tools, and I created that by clicking on New Library, and then creating a new tool. The settings you're seeing here are to suit a very cheap V-shaped router bit, and you can pause the video and copy them into Match. With this highlighted, we're now going to click OK. Our step over resolution doesn't need to be changed, but our depth per pass needs to be reduced dramatically. Typically with a PCB, I only want to cut something like 0.15 millimeters to cut cleanly through the copper surface. With this changed, we can click OK. Now that is depth per pass, but we also want to change the max depth to match this number. Instantly we get a preview, but if we click OK and then click on Show Simulation, we can rotate this around in 3D and we get a preview which is much more indicative of the final result. We can click Save G-Code and that'll give us a chance to create an NC file. Over to the router, and I'm using the SainSmart Genmitsu 3018 Pro, which I reviewed some time back. I have some blank PCB mounted to the machine, and remembering that the origin was at the lower left, I moved towards it. It's really important to make sure the PCB is clamped flat. Any flex at such a shallow depth of cut is going to ruin your results. For locating the top of the board, I like to turn on the spindle and then lower in very fine increments until I see and hear it just touch. In the host software, I can now tell it I'm at 00 for X and Y, as well as 0 for Z, and then I can start the cutting job. The feed rates that I've chosen and previously had on screen, I've determined from trial and error after making a few different boards. It's exciting to see your PCB take shape after all the time you've put in thus far. And for a board this small, it only took just over 6 minutes to complete. A pass with the vacuum cleaner reveals success, and a closer inspection reveals the circuit is free of defects. Now for cutting out the perimeter of the board, as well as drilling the holes, I could have imported data from KiCAD, but in the time it would take to generate the G-code and mount the PCB on a spoil board, I find it quicker just to cut it out manually. This machine is like an inverted jigsaw, and I can clean up the edges quickly afterwards on a linisher. The combination of these two yields a clean result. As for the holes, I have this set of mini PCB drill bits. Again, I could have done this on the CNC, but I feel that this is quick, convenient, and has less chance of me snapping them. All of this gives us our finished PCB, ready to install. Final step, let's get this onto the machine. After double checking my schematic to make sure I had the plugs the right way, I put everything into position and then used a set of helping hands to hold the PCB while I soldered all of the connections. Following this, we snip off the excess leads from our components to complete the board. The next problem is where to mount this board to the printer. I've made it as small as possible, but it's still too big to fit behind and out of sight. Therefore, I decided to mount the circuit on the end of the extruder stepper motor. Here I had some bolts to play with and it would be out of the way of the printer's range of movement. So I quickly modeled up a simple two-part solution. It's designed to use longer bolts for the outer side of the stepper motor that holds on this blank plate, and that's simply to prevent the PCB from shorting on the metal stepper motor. The PCB just fits inside the case, and the case has access to adjust the trim pot, as well as an entry and exit port for my 3 sets of wires. Before installing in the case, I had to sort out the length of the wires. The original 24 volts that went to the fan now goes to the input of this circuit. The thermistor comes out of the new PCB. I poked a small hole in the side of the silicon heat sock and it sits nicely inside there. Finally, the output from the board goes across the bottom to the original 24 volt fan. And when everything's installed properly, it looks like this. I would say relatively unobtrusive and still quite compact. But does it work? We can see the printer power is on, but the fan is stationary, so let's wake up Octodash and use it to heat up the hot end. When the temperature gets to the mid 40s, the fan comes on exactly like we would hope for, and as the hot end cools down, the fan starts to slow in the 40s and comes to a complete stop at just under 40 degrees Celsius. And for me, this little upgrade completes the printer. I can now leave it sitting idle with Octoprint running, but the screen will turn off and there isn't any fan noise. Thank you CHEP for an awesome circuit design, and let's hope some of these changes make their way onto the final product delivered to Kickstarter backers. Before you jump to the comments and tell me how bad I am at designing PCBs, remember that the methods that I used were to suit this type of home manufacture. Ultimately, I think it's fairest to judge me on the results, and in this case, that's a product that works 100% as it should. If you want to learn how to do this properly, CHEP has told me that he's preparing his own guide on making PCBs at home, so you should be sure to check that out. As for this machine, it's soon to receive a complete overhaul to extend its convenience as well as capabilities, so look out for that in the near future. Have you ever made a PCB at home, or maybe this video has given you the courage to have a go? Please let me know down below in the comment section. Thank you so much for watching, and until next time, happy CNC machining. G'day, it's Michael again. If you liked the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.